everybody, welcome back. Today I'm going to answer one of my lovely viewer question. It's a question about a statics problem from my static review session, and I hope it is helpful for you as well. So this is the problem. It's a little bit blurry here on purpose. And the problem says why you didn't use the moment 20 kilonewton meters at B in the second question. Thanks. I will have the link from that review session underneath this video. And the short answer to this is because the moment at B is the same. It becomes a constant. And another thing that I want to add is that since you're asking about the moment at B, you should also ask why aren't we adding the reaction at point D? In order to do this properly, right, to take the moment about point A, and to do this the way we're supposed to do it, we have to calculate first reactions and add all the forces. But we didn't do that because the problem is stating that we're doing all of these changes while maintaining the same reaction at support D. So the simple way to explain this is, let's say moment at point A equals to 7. That's before we make the changes. And a moment at point A after we make the changes, let's say equals to 5. So we have to find the difference between 7 and 5. The difference between 7 and 5, you're going to do 7 minus 5 equals 2. And that's without adding this moment at B. Now I can add the moment at B. I can say, well, the moment at A before we make the changes equals to 7 plus 20. So I get 27. And the moment at point A after we make the changes equals 2. Now I have 5. And this is the moment at B I have to add it, equals to 25. And now we're asked what is the difference between 27 and 25. And I'm going to get the same answer, 2. And this is why, in this case, it doesn't really matter because the reaction at D and the moment at B act as a constant. And now I'm going to go over the problem and we're going to try and solve it again without adding the moment at B. And then we are going to solve this problem adding the moment at B. So let's start all over. I'm going to read the problem. A frame ABCDE is supported by a hinge at A and the roller support at D as shown. If the 30 kilonewton force at C, they're talking about this one, and the distributed load over DE is to be replaced by a vertical acting upward force at C. So they're saying these two forces, if we replace them with a force acting upward at C, 12 kilonewton force, while maintaining the same reaction at support D. What is the additional moment that must be applied at C? It's a lot of information all at once, but we're going to take it step by step. So what I did last time, in order to solve this, we are going to take the moment about point A without calculating the reactions because we are told in the problem that while we're doing all these changes, the reaction at D is the same. I can show it up here. I'm going to say reaction at D. So let's first take the moment about point A before we make all these changes. Let's say moment at point A before we remove the forces. And this is going to be equal to, I'm going to choose clockwise my positive direction. So I'm going to have 30 kilonewton force. It's rotating clockwise direction about point A. 30 multiplied by the arm, it's 1.7. And then we have plus this distributed load. We have 4 multiplied by 0.8. And this gives me the resultant force, which is in the middle. And then we are going to multiply by the arm, which is going to be 1.6 plus 0.6 and plus half of 0.8. So half of 0.8 is 0.4 plus 0.6, that's going to be 1 plus 1.6, going to have 2, we're going to have 2.6 meters. And I stopped here last time, and I'm going to stop here for now. And this, let's say, gives me, if you do the math, I'm going to go ahead and do it quickly, have 30 multiplied by 1.7 plus 4 multiplied by 0.8 and multiplied by 2.6 equals, I get a moment about A before we remove the forces of 59, 32, and these are kilonewton meters. And now we're going to take the moment about point A after we remove the forces. And I'm going to do it in color red, sum of moment about point A after we remove the forces. This is what B and A mean. Maybe I should say after equals 2. So now we don't have these forces anymore, right? We remove them. We only have this 12 kilonewton force going upward. And this is counterclockwise, so I'm going to add minus 12 kilonewtons multiplied by the arm, which is 1.6 meters. And I'm going to ignore this 20 kilonewton meters this time. So I don't have any other forces, which means the result is what 12 newtons multiplied by 1.6, and I get 19.2, and it's negative counterclockwise, 19.2 kilonewton meters. So this is what we were last time, and what we did last time, I said, what is the additional moment that must be applied at C? The way we do that, we're gonna draw this system quickly, like this here. And we're gonna say, so before we remove the forces, I have a moment going clockwise of 59.32 kilonewton meters. And then for the second after we remove the forces, my system looks like this. I have a moment counterclockwise of 19.2 kilonewton meters. And we were looking at these two systems last time, and we said, how do we make them equivalent? How do we make them the same? Well, if you think about it, in order for these two systems to be the same, I'm going to start by adding a moment downwards of 19.2 kilonewton meters. And that's going to get me to 0, right? And in order to get to 59.32, I'm going to have to add another moment going downwards of 59.32. Does that make sense? I hope you're following me. If not, please leave a comment below and I will get back to you. More explanations. So now looking at this system, in order for these two systems to be equivalent, I'm going to have to add to this system number 2, where I'm removing these forces and I'm adding a 12 kilonewton force. I have to add, or maybe I should say, well, so this is the force system that has this 30 kilonewtons here and this distributed force here, 4 kilonewtons over meters. And then this system has a upward force at point C of 12 kilonewtons. And in order for them to be equivalent, I have to add a moment at C equal to 59.32 plus 19.2, and it has to be clockwise direction. So 19.2 plus 59.32 equals 78.52. And this is, we have to add it clockwise. So the correct answer is C, 7852 kilonewton meters clockwise direction. This is the moments that must be applied at C in order for the second system to be equivalent with the first system. That's what I did last time. And while we're at it, we can actually, you can assume a value for this reaction at D. We can say that this reaction is, let's say, 10 kilonewtons. So now we're going to do the same thing, but we're going to include the moment at B and the reaction at D. All right, let's do this. I'm going to say the moment at point A before we remove forces. These two forces, 30 kilonewtons and 4 kilonewtons over meter forces. So the moment at A is going to be 20 kilonewton meters. I'm going to add the moment at B first. So 20 kilonewton meters. And again, clockwise is going to be my positive direction. And then we have plus, I'm going to add this 30 kilonewton force, 30 kilonewton force, multiplied by the arm, which is 1.7 meters, plus I also have this distributed load, which is 4 kilonewtons over meters multiplied by 0.8 meters and multiplied by the arm, which is 2.6 meters. And now we have the reaction at D, which is negative, have minus, because it's counterclockwise direction about point A, right? It rotates this way. So minus 10 kilonewtons multiplied by the arm, which is 1.6 plus 0.6, and that gives 2.2 meters. And I am done with all the forces. So now let's calculate that. I'm going to have 20 kilonewton meters plus 30 kilonewtons multiplied by 1.7 plus 4 multiplied by 0.8 and multiplied by 2.6 and minus 10 multiplied by 2.2 and equals. So I have a moment of 57.32 kilonewton meters. And then sum of moments at point A, this is supposed to be moment at point A, after we remove the forces, equals 2. So in the second case, we are going to have, again, the moment at B, 20 kilonewton meters. Next, we don't have any other forces going in clockwise direction. I'm going to add minus 12 kilonewtons multiplied by the arm, which is 1.6 meters. And then minus, I'm going to add the reaction at D, 10 kilonewtons multiplied by the arm, which is 2.2 meters, equals. So now we're going to go ahead and do this calculation. We have 20 kilonewton meters minus 12 multiplied by 1.6 and minus 10 multiplied by 2.2 equals. So I get a moment going in counterclockwise direction, minus 21.2 kilonewton meters. Okay, so I'm gonna go to the next page and I'm gonna represent that. So we have first system, we have a support here, and we have a support here. And our loads, we have the 30 kilonewton load pulling this way. We have the moment that we took into consideration, 20 kilonewton meter load. And we have the distributed load. This is 4 kilonewton over meters. And of course, reaction at D. So this is before we removed the forces, and then we have another system after we remove the forces. I have the support here, the 20 kilonewton moment, kilonewton meter moment. And here we have a force pulling upward of 12 kilonewtons, and the reaction at D which is equal to 10 kilonewtons. We just assume that it's 10. There you go. And if I go back, so the first system, I got a moment equal to 57.32 going clockwise. And this is counterclockwise. 57.32. Let's represent this. So I get clockwise 57.32. I haven't checked this before, so I hope I get the right numbers here. And then this here, I'm getting counterclockwise direction, a moment of 21.2. I get 21.2. So again, we're going to apply the same thought process. In order for these two to be equivalent, first we're going to bring this to 0. So I'm going to apply a moment going downwards of 21.2. So that's going to bring this to 0. And then in order for them to be equivalent, I'm just going to add plus another moment going downwards of 57.32. And of course, the units are kilonewton meters. So, which means that in order for these two systems to be equivalent, I have to add a moment at point C in the second system of, so moment C of 21.2 plus 57.32. And I hope my calculations are correct, because I should get the same value, 57.32, 78.52 kilonewton meters. And this is how, and of course this is clockwise, right? It has to be in clockwise direction. It's important because our options, they give us an option of the same value on anti-clockwise or counterclockwise. So it's important for us to represent correctly the moments. And this is how I was able to prove to you that, or to explain to you why not considering the 20 kilonewton moment or the reaction at D, that we get the same result. All right, that was it for today. I hope this was helpful to you. If it was, don't forget to subscribe and give it a like, because this helps put this video in front of more people just like you. Good luck with your studying, my friends. I will see you next week.